I think I have over 1,000 videos on my YouTube channel now, so ring that bell. All right, Chemistry 3111. We're in the second of the four big chapters that we cover in Chemistry 3111. Keep in mind, this chapter 18, which is electrophilic aromatic substitution, and then chapter 19, which is this one, aldehydes and ketones. Then from there, we go into enols and enolates, and then we have another chapter on carboxylic acid derivatives. So those are 20 and 21. But we've already done 18, and now we're on 19. So we're kind of in the real meaty section of the course. There's a lot of reactions to learn in this chapter. In fact, before we started this slide presentation, I was showing my students the very last slide. Okay, this is the last slide. There's 102 slides in this chapter, and I'm not saying that to intimidate you or scare you. Look, many people have studied it before you, and many people are going to do it after you. So it's all good. But I just want to put this bug in your ear that we learn a whole bunch of reactions in this chapter. And we even learn some new functional groups. I'll just show you a couple here. Like this one we call an oxime or an oxime, depending on the person. We call this one an imine. We call this an enamine. We call this an acetal. We call this a thioacetal. We call this one a hydrazone. So we look at a whole bunch of different functional groups that you haven't seen before. So that's kind of interesting to learn some new functional groups. And as you can see, we learn a lot of new reactions in this chapter. So I don't know how far we're going to get today, but you know, another reaction that's going to show up is, you might remember this old chestnut, right? The Greenyard reaction. We already covered that in chapter 12. You also remember looking at lithium aluminum hydride reduction. I know we covered that in class. And we actually learn a very important reaction in organic chemistry. This reaction here is called the Wittig reaction. And the person who discovered that, so Georg Karl Wittig, he won the Nobel Prize for this. He shared it in 1979 with Brown, I guess, was the person he shared it with. So that's a kind of a neat one. And then we learned another name reaction here. This one is called the Baeyer-Villiger reaction. So I'll teach you about that towards the end of the chapter. So yeah, all kinds of cool stuff to learn in this chapter. Quite a bit of chemistry about acetals and hemiacetals. So we'll get into that. And of course, since the chapter deals with aldehydes and ketones, we're going to have to talk about the nomenclature of aldehydes and ketones, right? You've got to know how to name an aldehyde, and you've got to know how to name a ketone. So let's get into it. What they have in common, why are they both in the same chapter? Well, they both have a carbonyl group, right? Remember, I told you a carbonyl is just a carbon that is doubly bound to oxygen, and we call that a carbonyl group. It's found in an aldehyde. In an aldehyde, on one side of the carbonyl, we have an R group, right? Could be alkyl, could be aryl, that's not important. And on the other side, we have a hydrogen, just a proton. So that would be an aldehyde. And in a ketone, we have an R group. And on the other side, what do we have? Another R group, right? Two R groups makes a ketone like that. And these are very important compounds. They're, you know, pretty ubiquitous in biology and in industry. And you would have heard of formaldehyde because it's a gas at room temperature, but it's bubbled through water to make formalin, which is used as a preservative, and we still call it formaldehyde, but that's neither here nor there. It's this, and in fact, formaldehyde is the simplest possible aldehyde. Okay, you can't have an aldehyde simpler than this, CH2O. So there you go. So that's formaldehyde. That's its structure. And the next one is acetone, and I'm sure you've all heard of acetone before. You can buy it lots of places, right? Because it's used as nail polish remover. It's also used as a paint thinner. It's also used as a solvent, widely used as a solvent in organic chemistry. So acetone has many uses. Again, there's all kinds of places in nature that we find aldehydes and ketones. If you like the flavor of vanilla, no, I do. I like vanilla ice cream and vanillin. You can see this compound has not only has an aldehyde in it, but it also has a phenol, and it's got an ether in it. So there we go. We have an aldehyde in vanillin. If you like the flavor of cinnamaldehyde, or sorry, of cinnamon rather, cinnamaldehyde has a aldehyde group, and you can see that this is trans cinnamaldehyde, right? Because you have a proton going up and a proton going down. Anyhow, carvone, which is responsible for spearmint flavor, has a carbonyl of a ketone in there. We call this an alpha beta unsaturated ketone because there's a double bond down here. That's neither here nor there today. Benzaldehyde is almond flavored. Of course, male and female sex hormones. So you can see a couple of those here, progesterone and testosterone. And just the fact that they end in "-one" is a dead giveaway that they are ketones, and they both contain carbonyl. So how do you name an aldehyde or a ketone? Well, it's very similar to naming alkanes, alkenes, alkynes, alcohols, all those things. The first thing we do is we find the parent chain that contains the functional group. Then we identify the substituents, ethyl, ethyl, chloro, fluoro, butyl, sec-butyl, all that stuff. We give a locant or a number for each one of the substituents, and then we put all those substituents together alphabetically, and we put the parent at the very end. All right, so let's see here. Let's start with some aldehydes. For an aldehyde, you replace the suffix "e" with "al." So we go from butane to butanal, from pentane to pentanal, from hexane to hexanal, as you can imagine. And again, that parent chain has to include that carbonyl. So if you look at this hydrocarbon down here, yes, the longest carbon chain does contain 8 carbons, but it's not the case in this compound at the bottom right? Because it has to contain that carbonyl. And so we would call that hexanal. Notice that with an aldehyde, you don't have to call it 1-hexanal or 2-hexanal, right? Because there's no such thing. That since the aldehyde always ends with a hydrogen, it has to be at the very end, right? So we don't have to include a locant for an aldehyde. Something that I tried to introduce to you at the very end of Organic Chemistry 1 is that if you have other functional groups in the compound, like an alcohol or an alkene, the aldehyde is going to take precedence. Okay, an aldehyde, it's got a double bond to oxygen, so it has a higher, a greater hierarchy in the order of precedence of names of functional groups, I should say. And so we would call this compound an aldehyde and not an alcohol, not an alkene. And if you're wondering about naming this compound, I could get into that later if you want, but I would never ask you to name a compound this complicated with that many functional groups in it. So let's get back to something that's a little bit more straightforward. If we look at naming a ketone, we replace the E suffix with "-one", right? For aldehydes, it was E replaced with "al". For ketones, replace the E with "-one". And again, that parent chain has to contain the carbonyl. And notice that we go from butane to butanone. The same thing would apply with propane, right? We would go from propane, so this is propane. And then, of course, if you make a ketone out of it, that would be propanone. Now, notice that for propanone and butanone, we do not need a locant because the carbonyl has to be sandwiched in between 2 carbons. So there's no need to put a locant here. You don't have to call this 2-propanone. It's redundant, right? Because if you put the carbonyl on the end, it would be an aldehyde. Same thing here. If you put the carbonyl here, it would be an aldehyde. If you put it here, it would still be butanone. It's not till we get to 5 carbons. So watch very carefully. If we have 1, 2, 3, 4, 5, that's pentane. All right, once we get to 5 carbons, then we have to include a locant. This would be 2-pentanone, pentanone. And then if we had this compound, this would be 3-pentanone. So once you get to 5 carbons, you have to start providing a locant for your ketone. And we see that down here. This compound, this ketone, has 7 carbons in the chain. And so we put 3-heptanone, or you can put heptan, 3-one. Both are accepted by IUPAC. There's nothing wrong with either one. And you saw something similar to that when we talked about naming alcohols, right? We said this could be a 2-hexanol or a hexan-2-ol. Either one is accepted. Of course, if you have a chiral center, you have to designate that chiral center as being R or S. So if we look at this chiral center here, just a little practice here. The chlorine is going to be number 1. This will be number 4. This would be number 2, and this would be number 3. So we're going from 1 to 2 to 3. That's counterclockwise, which is S, but the proton is coming out in front. And so we reverse it to R. So that looks correct. So we would call this 2-chloro 3-phenylpropanal in the name. So we would have to put the stereochemical designation at the beginning. This is another chestnut here is if your aldehyde is attached directly to a ring, we call it a carbaldehyde. I don't know what to tell you other than memorize that. So we would call this cyclohexane carbaldehyde. You can imagine that if you had, something like this, you would call this cyclobutane carbaldehyde. right? If you had a 5-membered ring like this, you'd call that cyclopentane carbaldehyde, etc., etc. So a carbaldehyde, again, I taught the class long enough to know that I think you just should memorize that. And the next thing is that IUPAC also recognizes common names as parent names. So these are names that you should memorize. So I would memorize all of these here. Okay, and we're going to go over the systematic names as well. So formaldehyde, acetaldehyde, benzaldehyde. And so again, I think you should memorize the common names and the IUPAC names of the first 5 aldehydes. So this is with 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. So these are all aldehydes, aldehydes. And I would memorize these. Why? Because I learned the first time I ever taught this class years ago that it seems like the author of our textbook, he likes to mix up both. He likes to 1 minute include the common name, and then the next minute he'll switch over to the systematic name, or IUPAC name, I should say. So for IUPAC, it's pretty quick to remember those. You have methanal, ethanal, propanal, butanal, pentanal, right? So you have methane, ethane, propane, butane, pentane, methanal, ethanal, propanal, butanal, and pentanal. However, the common names not nearly as easy to remember. You have formaldehyde for 1 carbon, so methanal is formaldehyde. We already went over that one. The next one, acetaldehyde, that's what's largely responsible for producing the effects of a hangover, if you've ever had one before. Hopefully you haven't. The next one is propionaldehyde. So propionaldehyde, so you go from propanal to propionaldehyde. The next one, we go from butanal, and the common name is butyraldehyde with a Y in it. Notice it's butyraldehyde. And the last one, pentanal, is valoraldehyde. And the way my students told me to remember that is V, the Roman numeral 5. So you have valoraldehyde. So formaldehyde, acetaldehyde, propionaldehyde, butyraldehyde, and valoraldehyde. And again, their IUPAC or their systematic names are methanal, ethanal, propanal, butanal, and pentanal. All right, so you need to know all those. With that in mind, let's see if we can name some aldehydes here. We'll start with the first one. The longest carbon chain that contains the aldehyde would be this chain here that I have highlighted in yellow. I'll just delete that. And we'll number it off, starting here, 1, 2, 3, 4, 5, 6. So we've got a 5,5 dibromo and a 2,2 dimethyl. The bromo is going to come first. So we have 5, 5, dibromo, oops, 2, 2, dimethyl. And there are 6 carbons in the chain, so it's going to be hexanal, hex, and al. And remember, we had no common name for this. Okay, we only had the systematic name for this one. And it doesn't even say anything about common names anyway. All right, the next one, darn it, there's 2 stereocenters in it. Well, let's take a gander here. So we've got a total of what? 1, 2, 3, 4, 5, 6. So this is 3, 4, 5 trimethyl 2-hexanone. Let's scribble that down first. So it's 3, 4, 5 trimethyl hexanone. All right. And then let's see if we can figure out the stereochemistry of carbons 3 and 4. So it's going to be 3 something, 3 something, and then 4 something. Okay, so let's figure out, did anybody get stereocenter number 3 for me? Let's put the proton in here. So there we go. So this is going to be number 4. Let me just delete this. Somebody says it's R. Okay. I'll take your word for it, Tiana, but let me just check here. So this is going to, oops, son of a gun. What did I do? What was I here? Oh, there we go. Let's see. So this is going to be 1. This is going to be 2. This is going to be 3. So we go 1, 2, 3. That's S. We reverse it. You're right, Tiana. It's R. Let me do the next one. Tiana, did you get this? Did you get the other one? Yes. Or anybody? The other hydrogen is here. Wong says it's R. Okay, let's check. So we have so this is going to be 4. This is going to be 3. This is, sorry, this is 3. Son of a gun, can't see my 3. There we go. This is going to be 1, and this is going to be 2. So we go 1, 2, 3, which is S. What am I doing wrong here? Yeah, so that's S. So no. Okay, this carbon is attached to carbon, carbon, and hydrogen. There we go. That's my mistake. This one's attached to carbon, carbon, and hydrogen. So, son of a gun. So this group is going to be number 1. And this group is number 2. There you go. Fixed it. So 1, 2, 3. So that's going R. So we reverse it to S. There we go. All right. Sorry about that. And the last one, we have a cyclopentanone. So we would number that starting here. 1, 2, 3, 4, 5. So you'd call this 2, 2, 5, 5, tetra, methyl, cyclopentanone. Boom. There we go. All right. So a little nomenclature there. Let's try some. These are diketones and triketones. I didn't even go over the rules for these. I'll just kind of show you very quickly. If you have one carbonyl group, like we've seen so far, you call that an one. If it's 2, you suffix it with dione. If it's 3, you call it a trione. You can see what I'm doing here. 4 is a tetrone. Tetrone. I guess it's tetraone. Anyhow, there we go. Let me move this out of the way so we can think clearly. Oops. So let's just put it over here. And so for this first one here, you have a cyclohexane. And so you would number the carbonyls as 1, 2, 3, 4. So you'd call this 1,4 cyclohexane dione, the suffix you would use here. This one here is also symmetrical 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'd call this 258. 258 nonane trione. That might be worth the value of like 1 multiple choice question on a quiz, maybe 1. Okay, the little dione or trione thing. All right, there we go. So before we take a break, what I would like to do is kind of do a little review with you and cover all the reactions that we've looked at so far that involve the formation of aldehydes and ketones. So you've actually learned a few ways to make aldehydes and ketones. Some of this we have to go all the way back to organic 1. But if you remember this, we covered this in chapter 12. We learned how to make an aldehyde from an alcohol, primary alcohol, using PCC or desmartin periodinane or the Swern reaction. Hopefully you remember this guy here. This is called the Swern oxidation, right? So we know how to make an aldehyde that way. Then we looked at ozonolysis way back in organic 1 in chapter 8, the alkenes chapter. We said if you treat an alkene with ozone followed by dimethyl sulfide, right, that will make a pair of aldehydes in this case, as long as you have a hydrogen on one of the sp2 hybridized carbons, right, that will give you an aldehyde. Then we looked at how to do an anti-Markovnikov addition of water to a triple bond to an alkyne. And of course, that will make an enol, which will look like this, right? But that enol undergoes tautomerization to give you an aldehyde. So we looked at that. So the first step is going to be using a hindered borane like 9-BBN, okay, and then hydrogen peroxide and sodium hydroxide. So we covered that one. Then as far as ketones go, we said if you oxidize a secondary alcohol using chromic acid, PCC, Swern, desmartin, they all do the same thing. You would oxidize that to a ketone. We said if you did the ozonolysis of an alkene, but if you have a tetrasubstituted alkene where you only have R groups attached, in that case, you'd end up with a pair of ketones. So again, that goes all the way back to chapter 8, the alkenes chapter. Then we looked at the synthesis of a methyl ketone from a terminal alkyne. Remember, terminal means you have a hydrogen on the end. And this is a reaction we don't use a lot, but it comes in handy when we need it. And it's just a Markovnikov addition of water across a triple bond. and we use sulfuric acid and water, but you also need mercuric sulfate or mercury 2 sulfate. And of course, that also makes a enol, but it's a different enol than before. And that enol undergoes tautomerization to give you the methyl ketone. So again, that's covered in chapter 9, the alkynes chapter. Then the last chapter, hey, this is near and dear to your heart, right? We learned Friedel-Crafts acylation, which is a way to make a ketone directly from an aromatic ring in an acid halide, or an acid chloride, I should say, in a Lewis acid. So we covered that. And so with all that in mind, we could use any one of those reagents that we've seen before to affect these transformations. So we'll just kind of run over this quickly. The first one, if I want to convert a secondary alcohol to a ketone, in A, could anybody give me their favorite reagent for that? I'll take anything. There you go. Thanks, Tiana. Let's just write it over top. PCC. There we go. All right. And if, like, let's say Maria said, well, I chose desmartin peroxidine. Well, that's fine too. Let's say maybe Chaylin said, well, I'm a real SWRM kind of person, so we'll do oxalochloride and DMSO in the first step, and then the second step we treat it with triethylamine. Triethylamine, that works too. Okay, any one of those. What about the next one? If we want to take a primary alcohol and make an aldehyde, what do you got? Give me a reagent. I'm not fussy. Anybody have an idea about this one? It would be the exact same thing, wouldn't it? Right? Exact same thing. What's going on here? Come on. Somebody wrote same. Yeah. That works. Paste. There you go. It's the same thing. What about the next one? The next one, we want to do a Markovnikov addition of water across a triple bond, and that will give us, this enol, which undergoes tautomerization to give us the methyl ketone. So for that, we need sulfuric acid, water, and we need mercury 2 sulfate. All right, and the last one is the anti-Markovnikov addition of water across a triple bond, which will give us this enol, which undergoes tautomerization to give us the aldehyde. That's two steps. Number one is going to be 9 bbn. And step 2 is the same as any hydroboration oxidation, is hydrogen peroxide and sodium hydroxide. Boom, there we did it. All right, so now we're into something brand new, section 19.4, where we're going to start looking at nucleophilic addition reactions.